Hello, everyone. Everybody hear me okay? Good deal. Anybody have any questions while we're waiting for anybody to get in? All right. So last time we finished chapter 25. Today we're starting chapter 26, which is on DC circuits. I will warn you, probably the biggest things from this chapter are your ability to solve basically 2, 3, maybe even 4 current circuits. So in other words, DC circuits with resistors in various configurations and batteries in various positions, and you're going to try to determine the unknown current. In order to do so, you're going to have to use something called Kirchhoff's law, Kirchhoff's loop rule, and Kirchhoff's junction rule. And that's going to allow you to make some equations that are essentially equivalent to conservation of energy. And for each current that you don't know, you have to have one equation. So one equation for every unknown, just like the fundamental rule of algebra. So you're going to have to solve systems of equations. Now, I will probably need, like during the midterm or something, you'll have to show me at least one instance where you can solve that system of equations by hand. In other words, multiply an equation 1 by something, multiply equation 2 by something else, and then adding equation 1 and 2 to eliminate one of the currents, that kind of thing. Then you can sort of like what we did with the Atwood machine. So you got to make sure you can do that. Once you've done that on like the midterm, then you can use, Kramer's rule or Gauss-Jordan method, or, any kind of matrix multiplication that you want to try to solve systems of equations. You can even do it numerically. I don't care. I just need to make sure you guys can do that. And it does turn out to be something super important. For instance, when I was taking my graduate level graduate level solid state physics course, we had, for a project for the course, we were supposed to basically duplicate the research that was done that won some people a Nobel Prize in like 1972. And basically, it was horrible. It was 100 by 100 matrix that we had to what's called diagonalize, which is essentially the same thing as finding its inverse or something like that, like you might have done in pre-calculus. But of course, we got to use a program called Mathematica. But still, you had to actually be able to derive the setup of the individual matrices so that you could have all the components of the 100 by 100 matrix. And then, of course, then you had to diagonalize it. It was brutal. So it is still a very important thing. We, in fact, a lot of quantum mechanics is done with that by that way. So that's why it's sort of important for you guys to make sure you can do that. Now that we've got more people in here, does anybody have any questions before we get started on new material? Nada. Hopefully everybody got their test done. We got another test coming up. I'll have to remind you, but I want to say I planned on it being due by Sunday or Monday at 12:01 a.m. or something like that of this coming week. So that's the test 2 that should be on 24 and 25. So hopefully you're in a good spot there. I updated our Canvas page, and I noticed that some of the links I had left unpublished, but now we're up through next week. Even I've got next week's up there, as well as some as well as some relevant links to my YouTube channel. So for instance, I've got some problems in there where you're using Kirchhoff's loop rule and Kirchhoff's junction rule, where you're solving a system, DC circuit system for 3 currents. I've got you making a galvanometer, or excuse me, using a galvanometer to make an ammeter, and then using the galvanometer to make a voltmeter. I've got how to basically compute the process of charging up a capacitor as well as the process of discharging a capacitor. So all those are already linked and already on my YouTube channel. So there's problems just like what we do in the actual textbook as examples. So y'all can check those out at any time. All right, last call for questions because I'm getting ready to start cracking. Oh, got another student coming in. Okay, so if I can stop yawning. I've had a rough couple months. I'm just freaking tired all the time, and I came home today and took a nap, thinking that would actually help, but that didn't help. It made it just worse. All right, so here's the deal. We've learned about batteries. I told you how you can make them with just two dissimilar metals. You know, submerge, say, in a electrolytic solution. In other words, you know, salt water or Gatorade or something like that. Sugar would be kind of a problem, but I mean, you could still do it. It's just it'd be icky. So, anyways, two dissimilar metals, and the more stacks you have of them, the larger the voltage gets, and that would actually create a voltage. Well, it turns out when you actually make such a battery, that over time they die. And your book talked about, for instance, when you had the I think it had a carbon rod and a zinc rod or something like that. The actual atoms of zinc would break off the zinc rod and float around in solution, and then they'd either gum up the process or even cover up the carbon rod. So stuff like that happens, and what we do is we model it by having an internal resistance. And the neat thing about that is it works exactly like it should. For instance, when we take a battery like a AA, if you actually measure one with a voltmeter, you'll get a AA is usually brand new, is like 1.75 volts when they're supposed to be, you know, 1.5 volts. So they're usually a little bit higher. But then when you hook them up to a circuit where current's drawn out of it, the voltage across the battery will reduce. It might start reading 1.65 instead of 1.75, or if it's older, it might even start reading 1.5 flat, and that's when you know you've got a limited time left on the battery because it needs to maintain 1.5 for most circuits to work. So the way we model that is we pretend there's an ideal battery inside the battery, and the voltage of that is the EMF. And then right next to that, still inside the battery, is a small resistance. We call it internal resistance. And what happens is, remember, V equals IR, and V is the voltage drop going across the resistor. So, you know, the battery like steps you up to a height of, say, 12 volts, right? And the lower side of the battery was 0. And then you go through a resistor and that steps you down a little bit. Well, that exactly explains the fact that the voltage across the terminals of the battery decrease when you connect a current through it. Because if no current's going through it, the voltage, there's no current running around, so there's no decrease in voltage across that internal resistance. So it just reads the whole EMF, which, like I said, might have been 1.75 volts. So let me give you an example of that, and we'll go from there. Then I'll show you some resistances and stuff of that sort. So let me turn on my docket cam. And let me stop yawning. I want y'all to see one more time so y'all can yawn too. I know it's contagious, and I think that's just fun for me to have such an impact on my students. All right. So here you go. So what we imagine, for instance, is a battery, and I actually made up examples and worked them out a priori just to make sure I don't, you know, be such a loser and make a mistake like I always do. So we'll call this example 1. And I'm going to make that L really big so that it looks like an L instead of an E. Example 1. So here's my little battery. I wisely chose, notice I'm using that script E. That's what we use for EMF. And I'm just saying that's sort of the ideal battery voltage, which is 12.0 volts. And then right next to it, I put a very small resistance R, which is 1.0 ohms. That's the internal resistance. I'll draw a little dotted line figure around here to make some more sense of this. But then I go around to the actual load, which the big deal with the load is generally the load is much higher resistance than the internal resistance, or you need a different battery. So in this case, the load R is going to be 71.0 ohms. Now, if you picture this as a AA battery, what we mean is right here, say, would be the little bulb, the nipple that's sticking out. right here would be the lid. And that's what the battery's like. So you can see sort of it's a AA battery. When this circuit isn't connected, there's no current running anywhere. So the voltage is just, this is all one big conductor. So this voltage is V and this voltage is 0. But once you connect a circuit and complete the circuit, then current is actually flowing around it like this. And that current multiplied by 1 ohm tells you how much the voltage drops. So it'll go from 12 to here at this point to 12 minus I times R at this point. So that would be the terminal voltage. Well, actually, technically, the terminal voltage would be 12 minus I times R minus 0, because there's no given rule that says the bottom of one battery has to be 0. That'll make more sense when you start to see multiple batteries in a circuit, and you'll be like, well, where's the 0 voltage? Well, you don't know. Sometimes you have to work that out. So what we can see here is that we have basically a 12-volt battery. So that's sort of our height, if you will. So we went from here to here. I climbed up the mountain 12 volts or 12 meters or whatever you want to think. Then I have to go down I times 1.0 ohms. Now this is a series circuit. So every, let's say every electron that leaves this end has to go through that resistor, and then has to come through this end, go through that resistor, and then comes back here. Or you can pretend it's positive like we normally do, and then all the positive charges are moving around that way. The main thing is conservation of charge dictates the current is going to be the same through all of them. And then it's going to step down further, because that's got to be the rest of the resistance. So it's going to be I times 71.0 ohms. And then I'm back to my original height, which is 0. That's actually a conservation of energy, right? You see how we sort of, remember I treated voltage like it's potential energy is related to height. So what we're saying is, hey, the battery stepped us up 12, this stepped us down some, this stepped us down the rest of the way, so we're back to 0. So if you do this, you can then say, okay, well, 12.0 volts is equal to I times 72.0 ohms, and you get I is in fact equal to 12.0 volts divided by 72.0 ohms. I don't know why I wrote a volt there. Now, that's 12 divided by 72, which is essentially 1/6. I happen to know that 1/6 is 16.666666 or 16 2/3%. So I know this is 0.166, 3 sig figs, 3 sig figs. So I'm already done on sig figs here. I'll carry 1 extra sig fig, and that's the amps. Of course, we'd probably prefer to write that as, actually, no, I won't write it that way. I also should not be writing with this pen. I'm using my non-erasable pen. It should be written as 166.7 milliamps. So that's another way I can write it. Does that make sense to everyone? Oh, crap. Sorry, I disappeared there for a second. All right, so I got the right pins now. So what we're trying to figure out here is what is going to be the terminal voltage of this battery, and what is going to be the total current going through it. And just for fun, let's figure out how much power is lost from this internal resistance and how much power is lost, say, from the load itself. So we just found the current, and that was the key part. So I'm going to say A, the answer is 166.7 milliamps. And everybody knows the sign that when I have an underlined digit, that means that one's not significant. So we've gotten the current through it, and we actually, you might have seen something. It looks like we can add resistances when they're in series, evidently, and we'll work on that next. B, the next part is, what is the terminal voltage? Well, again, what I like to think about is little heights. And for instance, I could put right here at this end of the battery, which is one terminal, I'm going to say it's 0 volts. You're allowed to put the 0 volts anywhere you want, okay? But once you put that one spot, it's not necessarily true if you try to put a 0 somewhere else. That's not necessarily going to work out. You have to follow the rules. So right here, I know the voltage is going to step up 12. So right here, I'd say this is 12.0 volts. And then right here, since that one's 0, this would technically be V terminal. because it's technically this number, whatever it is, minus that number. That's what V terminal is. So if I call this point A and this point B, then V terminal would be the voltage at A minus the voltage at B. But since voltage at B is equal to 0, I get that. Okay. So can anybody tell me how I might get the voltage right here? By what amount, say it changes?
Use the current to using Ohm's law to find the voltage across the resistor, and then
exactly. Because what you got to remember is resistors are steps up or steps down in voltage depending on whether you're going the direction of current or not. We know the current, the conventional current's going around this way, so the resistance is a step down. So all I got to do is say, okay, well, I'm 12 here. If I find out how much this steps down, I just take it away from 12, and that'll give me my voltage at that point, which, because this voltage is 0, we know is the total voltage or the terminal voltage. So exactly right. V little r is equal to I times little r. Well, that's equal to 0.1667 amps times 1.0 ohms. And now you got that this is 0.1667 volts is how much it's going down. So V terminal, which is technically, like I said, VA minus VB, but VB is 0. The VA is going to be 12.0 volts minus 0.1667 volts, and I get 11.83 volts for that. So there's part A and there's part B. Does that make sense to everyone? Now what you know is, since we're pretending the wire resistance is really, really low, in principle, then this should be 11.83 volts here, and this should be a 0 volts there, and that would actually give us the voltage drop. And in fact, if you did do 71 times 0.1667, let's try it out. So 71 times 0.1667, I get 11.84 roughly. So that is clearly exactly what we expect. We expect the voltage to drop down to 0 here, and then that means that point 0 and all the way around here is 0 again. Does that make sense to everyone? So that's why I keep referring you guys to thinking about going uphill and downhill when you're talking about voltages, because you can always draw these little bubbles and sort of figure out what the voltage is at different locations. Now, the last part of this is I want to figure out how much power is wasted in the internal resistance. Remember, P equals IV, or P equals I squared R, or P equals V squared over R. Those are the three versions we can use. So I happen to know R is the same for all of these. That's the 166.7 milliamps. So I can say power wasted in the internal resistance is just going to be I squared times little r. Well, that's going to be 0.1667 amps squared times 1.0 ohms. And if I put that in my calculator, I get 0.02778 watts. Okay. So that's the power dissipated by the internal resistance. And that's, ultimately what is going to deplete the battery over a large period of time is you're constantly going to be wasting energy. And eventually that energy is going to go to close enough to 0 that you can't get any more out. Now, to give you some perspective, though, the load, which is a larger resistor, is going to be PR, which equals I squared big R. So obviously it's going to be 71 times larger. So it's 0.1667 amps squared times 71.0 ohms. See how I did that? 71 times bigger. It's like I'm a brilliant person or something. Okay, I'm making that up. But anyways, it's 1.972 watts, and that's P. Whoa. That's P big R. So that's it. That's a very typical, straightforward internal resistance problem. And like I said, it gives you an idea of what we model this battery as is over time, this resistance can get larger and larger and larger. But even if you didn't do that, you'd see that over time, you're still going to wear the battery out because you're drawing power out of it every time you draw a current. So, and you can feel that if you've ever seen batteries when they're actually being used, they normally get a little warm. Have you ever felt the back of your cell phone get warm when you've been talking on it a while? That's the same deal. All right, so now that we've got that down pat, I need to square up some stuff regarding resistance. So we're going to go into derivation mode. So first off, I'm going to imagine a series of resistors in series with a voltage V. And then that's going to run around the corner, and I'll have a resistor R1, resistor R2, resistor R3, okay, and leaving this, we'll just assume there's a current I. And from what you've learned in lab, you should know, how is this current related to the current through R1 or through the current through R2 or the current through R3? Does anyone know?
Current's the same through all of them.
Exactly. That's the nature of series. The charges have no alternative path to follow. So I1, I is equal to I1 is equal to I2 is equal to I3. Now, what we're going to do is replace this with some equivalent setup that the battery wouldn't notice any difference. It still says, oh, well, my voltage is V and I sent out a current I, but I think there's just a resistance R equivalent sub S. Okay, that's what we're trying to calculate. What we do know from our lab as well is that this is a voltage increase, 0 to V, and then from V to a new voltage is a voltage drop, V1, and then another voltage drop, V2, and then another voltage drop, 3. So we get that V is equal to V1 plus V2 plus V3. Does that seem right to everyone? What I basically did was the same thing I did here, but I put the minuses on the other side. So basically I'm saying the voltage of the battery minus the voltage of resistance 1 minus the voltage of resistance 2 minus the voltage of resistance 3 brings me back to 0. Only I put them on opposite sides. So hopefully everybody agrees with that. Now I can use Ohm's law, which says V equals IR. And using those two, I get I times this guy, which is R equivalent S, is equal to I times R1 plus I times R2 plus I times R3. And the reason why I did that is because we already found out that I1 equals I2 equals I3. So now I have that R equivalent in series is equal to R1 plus R2 plus R3 plus ... As you can tell, if I did this with 84 resistors or 42 resistors, I'd still get the same result. All right, I just keep adding them. I hate my uppercase cursive D. Looks like he's got too big of a forehead. Anyways, he's falling over. Oh, my head's too big. Okay, now let's consider the one in parallel. So we've got a formula for series. Notice that series, by the way, is exactly the same as what we got for parallel with capacitors. So capacitors and resistors are sort of opposite sides of the same coin. They sort of do the opposite thing. For capacitors, we got 1 over C equivalents equal to 1 over C1 plus 1 over C2 plus 1 over C3 for the equivalent capacitance in series. Now you're going to see we're going to get something just like what they got for series, but we're going to get it for parallel now with resistors. So I'm going to do again a voltage V, a current I leaving it, and that's going to run into a resistor R1, a resistor R2, and a resistor R3. And of course, remember, this is I1, I2, and I3. What we've also learned in labs, hopefully by now, is that this current is basically a certain number of charges going past, say, a certain spot every second. But when it gets here, it's got a choice. Some number of them will go here and some number will go there. But the total number, this one plus this one going every second, has to be the same as that. Similar, when it gets here, it's got some number going here and some number going there, so that what you ultimately find is I has got to equal I1 plus I2 plus I3. That's just conservation of charge. Does that make sense to everyone? We also learned in lab, however, if we put a little bubble right here, the voltage is V. We put a bubble right here, the voltage is V, V, and V. If we put a bubble right here, it's 0, 0, 0, and 0. So you see that V1, V2, and V3 are all equal. And then we can also use V equals IR. And with all this stuff combined, we get a really neat result. Well, I is equal to V over R. So that's going to be V over R equivalent. I didn't draw R equivalent this time, but it'll be R equivalent P. But what I'm really doing is I'm replacing it with same current I, R equivalent P. So that's the equivalent circuit. So V over R equivalent is just I, which is what this part right here is. And since V1, the voltage across resistance 1 is just V as well, so that's going to be V over R1, and that's going to be plus V over R2 and plus V over R3. So ultimately we get 1 over R equivalent in parallel is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus ... because we can see that that generalizes to just keep adding on reciprocals if the number is greater than 3. Any questions on that? So now what we see is when resistors are in series, the total resistance is equal to the sum of the resistances. When resistors are in parallel, the total resistance is actually smaller than any one of the resistances. The same but reverse conclusions that we made about capacitors. So if you want to make a smaller and smaller resistance, keep taking smaller and smaller resistors and put them in parallel with each other, and the equivalent resistance will get smaller and smaller. If you need to make a really big one, you just keep putting them in series. All right, now that we have that, let's try a bit of a conceptual example. Let's imagine we have a 12-volt battery, like you might have in your car, and we have 2 identical headlights. This will be example 2. We have 2 identical headlights. We can connect the headlights, which I'm going to draw as a circle with a resistor through it. We can connect them in series like this. Or we can connect them in parallel like this. Let's go ahead and call that 12 volts, say, just for a number. We're going to pretend like it's V anyways. So what I'd like to know is which one of these configurations makes the most light. Now remember, light is heat energy that's coming off of these light bulbs. You know, basically you're making a filament so hot that it's burning white hot, and then it bounces off of these reflective lenses in the back or reflective mirrors in the back. And basically the hotter it gets or the more power is wasted, the better off you are. So you can think in terms of P equals IV as what's going to give you the most power. So is the I going to be bigger here or bigger here? Can y'all tell that?
It would be bigger for the one in series, right?
So we have a suggestion that's bigger for the one in series. That might be right. And I think this is why he's thinking, right? This current is going to have to be broken in half, and each of them's only going to get a half current. And his logic's pretty good there. That's exactly what's going to happen, right? But remember, the total amount of current that comes out of this battery is related to the total amount of resistance. So which configuration has the largest resistance?
Putting them in parallel is going to lower the resistance, which would allow for more power. Is that correct?
Yeah, possibly. I'm going to actually put money where my mouth is by showing you, but yeah, you're actually all asking exactly the right questions, making exactly the right statements. You're realizing the reality of the problem, which is, okay, here, this is going to make a smaller resistance because resistance is add and reciprocal. So clearly the net resistance of this one's smaller. So the total current coming out of here would be larger, even though you are going to divide each current by 2 for what's the battery, for what the, excuse me, for, I don't know. I just became Elmer Fudd or something there for what each light bulb gets. Okay. This one, on the other hand, is going to have a bigger resistance, but each one's going to get exactly the same current. So yeah, that's exactly what we need to do. So let's think about it for a second, and I'm going to work out the details of this one. What I know is that V equals IR, right? So in this case, let's forget about 12. I'm just going to call that a V. Okay. And what I see is, since these are identical, the voltage is going to go from V right here to something else right here. And then that same thing right here. So you see the voltage is dropped to something. By symmetry, if I change these, it should drop by the same amount. So in fact, what you're going to see is each one has a voltage of V2, or excuse me, V over 2. Does everybody get that logic? Because the total amount it's got to drop across 2 must be V, and since they're identical, there's no reason for the voltage drop to be different on each one. So V1 equals V2 equals V over 2. So we now have the voltage. We want the current too. Now, what we know is the total resistance. Let's pretend the total resistance is R. Okay, don't need to know what it is, just call it R, and we know they're identical. So that says V is equal to I times, notice it's twice R. So now we can say I is equal to V over 2R. So that's the current through both of them. So I can say P in series is going to be V over 2R times V over 2. Does that make sense to everyone? So that ends up being V squared over 4R. Now let's try this one. We're going to again say this is R and this is R. However, in this case, the voltage for each one is just V because they're in parallel. So V parallel is just equal to V. Now, the current, we say V is equal to, now when you do 1 over R plus 1 over R, they're identical, right? You get 2 over R. So 1 over R equals 2 over R says that R is 1/2. So when you put two identical resistors in parallel, they become R over 2. So V is going to be I parallel times R over 2. So we can see that I parallel would be, of course, 2V over R. Make sure my math is right there. Yes, IP is equal to V over R. So now I can compute P for these two guys. Now that's just one of them. So I'll just do one here since I only did one there. Otherwise, I need to put a 2 in front of it because I actually get this much power for each light. So this is going to be P is equal to IP times V. So I get 2V over R times V, which equals 2V squared over R, which is in fact, this is the parallel case. So P parallel over P series should be 2V squared over R divided by V squared over 4R. And you see the V squareds cancel out and the 4R on top hits the 2R, makes 8. So you see that it's actually one light is 8 times as bright as the other from this configuration to that configuration. So yes, parallel is better. And that is the way they connect them in a car. Another good reason for connecting them that way in a car, you can ravel one headlight. I mean, you might get a ticket, but you can ravel one headlight. If I burn up this headlight, that literally means the filament melted. That's normally the case with original incandescent headlights, is the filament would break, which means it's an open circuit and no current could flow. Well, that would be a problem, right? One headlight burns out, you got no lights now. So yeah, that's another reason. So yeah, they are connected in parallel. Does that make sense to everyone? Okay. So we got that. And that's a nice, neat little excursion into everyday life. And that's sort of a conceptual problem. You didn't have to actually work that out. You could sort of reason it out. But at the end of the day, if you can't put it in some definitive mathematical framework, you might not be catching all the nuances unless you're just really good at picturing those things in your head. That's obviously where some problems come in. So any questions on that? Now, what you might want to do is say, okay, well, how much would, for instance, 2 light bulbs actually burn if you did put them in series versus parallel? So let's say we've got, now this is AC, but I'm going to say it's 120 volts. Okay. So that's 120 volts. It's actually we're going to pretend like it's a 120 volt battery. And we're going to put a 60 watt, 120 volt battery light bulb here. And then we're going to put a 100 watt, 120 volt light bulb here. And we're going to find out what the power dissipated is. So P60 equals question mark, P100 equals question mark. And then we're going to do the same thing with these two. In other words, the same light bulbs this time are identical light bulbs, this time put in parallel. And that's our symbols. P60 and P100 just means series. P60 parallel, P100 parallel means in parallel. So what we can do is we're going to basically say, oh, well, I know that the power, P, is equal to, for the 60 watt, the power is equal to 60 watts when it's connected to 120 volts. We know that P is equal to IV, which equals I squared R, which equals V squared over R. So that allows us to determine R with that last one. So with that in mind, we can say 60 watts is equal to 120 volts squared over R60. So our resistance R60 is actually equal to 120 squared divided by 60. Yeah, that's right. And I get 240 ohms. Similarly, the R100 is going to be given by 120 volts. No, I would do it right the first time. It should be, yes, 120 volts squared over 100 watts. And that gives me 144 ohms. So now we've got the resistances, and we're going to ignore, when I put it here, this is really not going to be 120 volts across that resistance, right? Across that light bulb, because now I'm taking the 120 and part of it's going to go across here and part of it's going to go across here to add up to give you 120. But I'm going to pretend like that resistance is roughly the same in all of these configurations. So that's a big assumption. It might not be that correct, but it's a first order approximation to trying to get the right answer. So now that I have that, I can now calculate the voltage for the 60 watt bulb. So we'll say for the series part, we got V60 is going to be equal to IR. Well, the R we know is 240, but the I is a little different. What we have to realize is in series, what we found was that the 120 volts is equal to I times 240 plus 144. That'd be what, 388, 384? Because they're in series, right? So 384. So I is equal to 120 divided by 384. That equals 312.5 milliamps. That's 312.5 milliamps. That's obviously one extra sig fig, but that gives us what we need. Now that we know that amperage, we can say V, the voltage across the 60 ohm, is 0.3125 amps. That's what that number is. Times the resistance, which is 240. So times 240 for that for that current, and I get 75 volts. Okay. From that, you can probably guess that the other one's going to be 45 volts because the net's got to be 120, but we're going to go ahead and calculate it anyways. So for the 100 watt bulb, I'm going to get 0.312. They're in series, so clearly the same current's going through them, but in this case, it's going to be 144 volts, or excuse me, ohms instead of 240. That ohm looked really horrible. So 0.312 times 144, that gave me 45.0 volts. Okay. So P60 is equal to 0.3125 amps. That's one extra sig fig times 75.0 volts. So 0.3125 times 75, and that gives me 23.44 watts. And P100, 0.3125 amps. times 45.0 volts is equal to 14.06 watts. So we're only getting about 37 watts out of those two light bulbs when they're in series. Now let's try and see what happens when they're in parallel. Well, when they're in parallel, 1 over R equivalent is equal to 1 over 140 or 1 over 240 plus 1 over 144. That's not a really nice thing to do. I'm going to work that out instead of do it in my head because that would be awful. So I'm going to say 1 divided by 240. That gives me 0.004166 plus parenthesis 1 divided by 144. Now that I've added them, I got 0.011111111. That's this side. Now I got to take the reciprocal of that. So I'll do 1 divided by that answer. And that gives me 90. Wow, that was a lot easier than I thought. So you can see the equivalent resistance was in fact smaller than either one. That's what I've been arguing about this, but this is just another instance of it. Now that we know the R equivalent, we can say that 120 volts is equal to I parallel times 90.0 ohms. So we get I in parallel is 120 divided by 90. And that gives me 1.33 amps. So now I've got the current there. Of course, all of these are going to have the same voltage. So the V for the 60 in parallel is 120 volts. The V for the 100 in parallel is 120 volts. So all I need now is just P equals IV. So P 60 parallel is going to be, we know that 1.33 amps is what comes out of here. What I got to figure out is what's the I in the 100 ohm resistor and what's the I in the 60 ohm resistor. So 120, let's say I and 60. So this one, I want to say that's 120 volts. And in this case, I'm going to say that's equal to, assuming the same resistance that we had before, that's equal to I 60 times 240 ohms. And then I 60 would be 120 divided by 240. That should be 1/2. So 0.500 amps. And then I 100, this should be 120 volts is equal to I 100 times 144. And hopefully the two add to give me 1.33. So in this case, I'm going to do 120 divided by 144. And I get 0.83333. And lo and behold, that works just like we thought it would, because if you add those two, you get 1.333. So now that we have that, we can say the 60 watt light bulb in parallel is going to give us 0.500 amps times 120 volts. And that's obviously going to be 60 watts. And then P100 in parallel is going to be 0.8333 amps times 120 volts, which I think you can tell is going to be 100 watts. And that's exactly right. So what we found out is, yes, that's actually the way we do connect things, is in parallel. And when we did do it in parallel, we did get the 60 watts and the 100 watts advertised, assuming the resistances, the 240 and the 144 didn't change. But when we put them in series, we in fact got a lot less. This gives us a total of 160. This gave us a total of 37.50. Any questions on that?
I noticed that the power dissipated in the parallel circuit is the resistance values and the power dissipated are the same. Is that a consistent pattern?
Yes, yeah, that's exactly how we connect them. And even, you know, that even came down to this calculation, because when they say a 60-watt light bulb is really meant for 120 volts, so you'll consistently get the resistance here so that it will give you exactly that wattage. So
That's
yeah,
cool.
whenever that's the way things are wired in a house, is basically in parallel. That's why they work out that way.
That's wild.
It's kind of neat, isn't it?
Yeah.
And this is sort of like I mean, these are not unlike the calculations we did with capacitors, but they're, you know, a little different, because when you do the reciprocals versus when you just add is different. But other than that, they're sort of the same thing. And you'll see that now. I'm going to do almost the same problem I did in class after I introduced how capacitors combine with other capacitors. I'm now going to do another one where we're actually computing how resistors combine with other resistors. So this will be example 4. I guess this was example 3. Okay, in this case, I'm going to just imagine a battery. And you might notice the pattern here. That's a 100 ohm resistor that runs into a parallel bank of resistors, one leg of which has 2 resistors in series, and the other leg of which is just one. And what I'd like to do is find out the equivalent resistance. And then, as you might guess, we're probably going to make this 120 volts or something and compute what the voltage is across all these things and the currents through them and all that good stuff, just like we did with capacitors. So first off, I'm going to say this is equivalent to, I'm going to ignore from here down back up to here. And we're going to say this is equivalent to the 100 ohm. Notice how I dropped the units right quick. It's obvious that you're talking about ohms since it's over a resistor symbol. And I'm going to replace this with 1 resistance and this with 1 resistance already, and like that. So this one's 400, but clearly these two are in series. So what's the resistance of both of them together in series?
$400.
Exactly. I think you said right. 500. Because 200 plus 300, or you might have misread mine. All right, now the next thing is I got 500 and a 400 in parallel. Well, I know, for instance, 1/5 plus 1/4, the least common denominator for those is 20. So that'd be 4/20 plus 5/20 be 9/20. This is going to be 9 200s basically. So with that, you can actually work it out to be 222. So now I can take this and say I've got a 100 ohm resistor, and what I just did there was 1 over R is equal to 1 over 400 plus 1 over 500, which is equal to, I'm going to multiply this one by 5. That's 5 over 200, because I'm multiplying by 5 over 5, or excuse me, 2000. And then I'm going to multiply this one by 4. 4 times 5 is 20, so that's going to make this 4 over 2000. So I get 9 over 2000. So R is equal to 2000 divided by 9. 1/9 is 0.11111. So 2000 times that gives me 22222. So that's how I got that. Carrying one extra sig fig. Now these are easy peasy because they're just in series. So now I know it's 322.2 ohms is the equivalent resistance of the whole thing. Okay. So that's one example. Example 5 is what are the voltages across. That's important wording to notice, by the way. It's voltages across and currents through. Each resistor. Okay. So what we first off can tell, let's say, assume, see if I like any of this. Let's say, yeah, let's say assume V equals 120 volts. That's not the best number. I was really looking for a number, but when I got this ugly 322.2, I'd pretty much crapped it out. So, oh well. All right. So what we know is we basically have the equivalent of this, which is 120 volts opposite a resistor of 322.2 ohms. And I is going through it. So I, which I'll point out is coming from here, is just going to be equal to V over R. That'd be 120 volts divided by 322.2 ohms. So that gives me 0.3724, which you could call 372.4 milliamps if I wanted. So I know the total current. That's nice. And of course, I know this is going to be 120 right here and 120 right there. And this, of course, will be 0 right here and 0 right here. Whatever voltage this is across here, I know the current going through it is this current, this 0.372. So if I take this 0.372 and multiply it by 100, I get 37.24 volts. So this part being 120 means right here would be 120 minus 37.24. Does that make sense to you guys? The current had no way of breaking apart before it got here. So all of the current coming out of here, all of this I has to go through that one. So I 100 is just equal to I, which is 0.3724. Implies V100, and that's the voltage across it. That's how much it drops, right? So it's 120 on this end, and then it's 120 minus IR on this end. So V for the 100 is going to be 0.3724 amps times 100 ohms, which gives me 37.24 volts. So now what I know is that 100 ohm resistor has a voltage of 120 here. And 82.76 volts here. Does that make sense? So in other words, if I do 120 minus 37.24, I get 82.76. Now, that also happens to be the voltage right here and even right here. And that 0 happens to be the voltage here. So now I know that the voltage across the 400 is 82.76 volts. So V400 is equal to 82.76 volts. That means I400 is just going to be equal to 82.76 volts over 400 ohms. And I get 0.2068 or 0.2069 amps, which is 206.9 milliamps for I400. And this was just plain I. Okay, so I now know the voltage there. Now I also know that 372.4 milliamps went in here and 206 went the bottom way. So I can figure out what went the top way, and that will allow me to determine the voltages of those as well. So I'll do it that way, assuming conservation of charge. So I know that I200 is equal to I300. In other words, the current going through the 200 ohm resistor and the current going through the 300 ohm resistor, they got to be the same because they're in series. But I know they're also equal to the total, which was 372.4 milliamps minus 206.9 milliamps. So that's going to give me 372.4 minus 206.9 equals 165.5 milliamps. Okay, so now I got the currents through those two guys, and now I can figure out the voltages, and we still got to check, because when I calculate the voltage of this and the voltage of this, it better be that 82.76 when you add them up. So V200 is equal to 160 or 0.165 amps times 200 ohms. I get 33.1 volts for V200, and V300 is going to be equal to times 300. That gives me 49.65 volts. So 49.65 plus 33.1 gives me 82.7. I had 82.7. I had 7.56 and I got 7.5. So yeah, that works. Okay, so that's almost an exact parallel to what we did with the capacitor when we first figured out those. Anybody have any questions on that? No question. Is kind of confusing. Let's go back over and just talk about what we did. Maybe sort of sum it up so that it makes a little more sense, because there's a lot of steps in that. So, and you don't always have to do it this way. In this case, I just sort of brute force tried to muscle my way through by understanding how voltage changed across resistors. Namely, if you go in the direction of the current, the resistance is going to represent a voltage drop. And then going from a short plate to a long plate on a battery makes a voltage increase. And I know the net voltage increase and decreases around any one loop is always going to give me a total of 0, because I got to step up, and then step down, and come back to the same height. So one way that can be done is you can sort of find the equivalent resistance of all these resistors, which is what I did. I took the 200 and 300. That's sort of the innermost embedded and simplest part to combine. That gave me an equivalent of 500. That 500 was in parallel with 400. So I worked out the parallel resistance formula to end up with 222 ohms. So I could replace this bank of parallel resistors, which was originally 3 resistors, 2 in series and 1 in parallel, with a single resistance of 222.2 ohms. And then I had a 100 ohm resistor in series with that 222. So the equivalent resistance really was 322.2. Far as the battery is concerned, it only knows there's 322.2 ohms of resistance over there. So it just supplies the appropriate amount of current given by Ohm's law. And that's 120 volts is equal to I times 322.2. That gave me 0.3724 amps, or 372.4 milliamps. Now that I have that current, then I can remember Ohm's law always tells us how much a voltage change occurs across any resistance if we know the resistance. So I noticed that the 372.4 milliamps that left here had no other choice but to go all through the 100. So the 100 ohm resistor, in fact, had to take every bit of that current and use it to change the voltage. And the voltage of that, of course, turned out to be 0.3724 times 100, or 37.24 volts. So that's how much the voltage changed from here to here. And since we're closer to the positive side, on this side, this is where the red terminal on your power supply or your voltmeter should be, and this end should be the black one. And then you read a positive number, and that voltmeter would in fact read 37.24 volts. Now, that being said, we know that right here to here, that's supposed to be 120 volts. So I just said it was 120 and that this is a 32.74 drop. So if I wanted to know the voltage right there, I'd have to take 120 minus 37.24, which is what I did. And I got 82.76. Y'all see the difference between the voltage across and the voltage at a location? That's sort of the weirdness of this. What you can think of this one as is if I stuck the black probe of my voltmeter right here, or stuck it directly in ground, which I'm assuming that's what this side is. And then I stuck my red probe anywhere on the circuit. That's what these little bubbles I keep popping up are. So that 87.24 that I drew right, or 82.76, excuse me, that one right there is what I would read when my red was here on the right side of the 100 ohm resistor and my black was over there. So this is the height, whereas this is the change in height that occurred to get there. Everybody understand that? Anybody have any questions on that? Okay. Now that was the case, I know that same current, that same 372.4 milliamps is going here, and it's going to break apart, and it's going to break apart in such a way that the majority of the current will go through the smaller resistance. And the way you think about that is clearly the smallest resistance is 400, not 500, but it's going to be such that they have the same voltage, V equals IR in both cases, where I would be big to account for this small r, and I would be small to account for this big r, right? So you do expect a bigger current to go through here and a smaller current to go through there. But because I was paying attention, I knew this voltage was 82.76, and I knew therefore this voltage was 82.76. I knew this was 0, which meant this was 0, this was 0, and even that was 0. So I actually had the voltage across the resistor, which is what we have to use when we use Ohm's law. Ohm's law is about the voltage across, not the voltage at a particular location, right? So all I had to do for the 400 was say, okay, well, Ohm's law says that 82.76 is equal to I times 400, and therefore the I through the 400 is 82.76 divided by 400. That should be a digit there. When I did that division, I got 0.2069 or 206.9 milliamps. Now, I could have done this another way. I could have, figured out what the voltages were for each of these and stuff like that. What I did was I used conservation of charge to realize that, okay, if 206.9 went this way and I had 372.4 total coming in, then all I had to do was take 372.4 minus 206.9, and that'd be the current going through both the 200 and 300 ohm resistor. That's what I chose to do. So 372.4 minus 206.9 gave me 165.5. That's the current going through this one, and that's the current going through this one. So unlike the way I did with the capacitor, I actually used conservation of charge to figure that out first instead of verifying conservation of charge when I was done. So then all I have to do is take that 0.1655, which is me converting it to amps, times 200. That'll be the voltage across the 200 ohm resistor, and then do the same thing times 400, or excuse me, times 300, and that'll give me the 300 voltage across the 300 ohm resistor, and that was 49.65. Now, to make sure that makes sense, I added those two, and lo and behold, it did give me the same voltage that I had before, which is 82.76, except I got 82.75. So that was the process that I used. It's not necessarily the best process. In fact, there's a really robust set of steps you're supposed to take. And when you take those steps, that's sort of the best way, or one of the best ways to do it. So let me show you what that is. So first off, I'm going to start off with Kirchhoff's loop rule. And I think I will use a blue pen. So Kirchhoff's loop rule. If anybody's ever learned from astronomy, there's Kirchhoff's laws about light and stuff like that. Basically, you can get a full spectrum. In other words, you remember when you shine light through a prism, it gives you a whole rainbow. And then if you then shine that light from a rainbow, or that white light that produced that rainbow, if you shine that through a cool gas, that cool gas is going to actually steal some of those wavelengths, and you get little black spots missing from the rainbow. Or if you then look at that cool gas that's been excited by that light going through it, you're going to get just a few bright lines that match where the black spots were earlier. Those are Kirchhoff's rules for stars. This is the same guy. That's the whole reason I told you that. It's the same guy, and that's sort of the nature of these physicists of the time, is they're pretty much doing everything. So Kirchhoff's loop rule is basically a conservation of energy. And what he says is the sum of the voltage drops and increases in any closed loop will add to 0. So that's Kirchhoff's loop rule. KLR. Okay. So that's what we were doing here when I said, okay, I'm going to go from here to here. That's going from short side to long side of a battery. So that's a voltage increase. Therefore, it jumped up 120 volts, 120, 120, 120, still 120. Now that's going to drop down 37.24 volts. So that brings me down minus 37.24. And then if I just choose to go this loop, I'm going to go over here and say minus 82.76. And then there's nothing else. And I get back to where I started from, I'll just say equals 0. That's all we mean. That's Kirchhoff's loop rule. And the rules are, if you go in the direction of current flow, and you're going to pick the current flow, by the way, you're going to pretend like you know what directions all the currents in the circuit are going. Once you pick them, you got to stick to it, though. So let's say caveat. So here's a caveat. 1, you often have to pick the current directions. Don't be afraid of guessing wrong. Because if you guess wrong, you'll find out later the equations will give you a negative answer for that current, and you just use that negative for the rest of the equations, and everything will work out fine, and you'll just realize, oh, I was wrong about that one. No big deal. Okay. 2, when crossing a resistance in the direction of conventional current, the voltage change is delta V equals negative I times R. So if you have this little resistor right here, say R1, and you said that I1 happens to be going that way, if you're going around the loop this way, then that's a voltage drop. But if you happen to be going around the loop this way, that'd be a voltage increase. Oh no, I think the pen just died. A resistance in the opposite direction of conventional current the voltage change I'll just say is positive IR. Okay, so that's your major rules there. Then I've got Kirchhoff's junction rule. Okay, and that says, I'll show it to you in graphical form. So these are going in. I'm gonna call that I1. I'm gonna call this I2. I'm gonna call this I3. Call this I4, and call this I5, and call this I6. So let's take all the ones that are going in. Well, I1's going in, so I'll say I1 plus I3 is going in. I5 is going in. And that looks like the last one. That's got to be equal to I2 plus I4 plus I6. So the sum IN is equal to the sum of I out. That's Kirchhoff's junction rule. And those two rules will allow us to set up any kind of circuit and solve it. I'm going to do, since we don't have enough time to do the next example, I'll draw it out real quick. And let's say, okay, let's say we have a 100 volt power supply right there. I'm going to say it's got a resistance of 1 ohm, internal resistance. And then over here, I'm going to say there's a resistance of, I don't know, 20 ohms. And over here, nothing. I'm going to say there's a 50 ohm resistor here and another resistor here of 1 ohm. And let's say this is a battery right here that has a 50 volt. That's a 50 volt source. And then let's say over here, there's a 40 ohm resistor. So this would be another type of example, say. What I would ask for is this has 3 possible currents. What are the currents? So you would come in and you'd have to draw the individual directions of the currents. I'm going to say and label them. So this one would be I1. I'm going to say I1 is going this way. I'm going to say I2 is going this way. And what the heck, let's say when this one gets here and here, okay, I'm going to say I3 goes this way. So I've had to choose those. So when I go to do Kirchhoff's junction rule, let's take this loop right here. I'm going to say starting here, Kirchhoff's loop rule. I think I said junction rule just now, but I meant Kirchhoff's loop rule. So I'm going to say plus 50. Notice I'm not even going to write units. Minus I2. I'm going the direction of current, so that's a minus. I2 times 1.00 minus I2 times 50. And now minus I3 times 40. I'm back where I am. That's going to be equal to 0. So that'd be one of my equations. I could do another equation this way. And in that case, I'm going to say 50 minus I2 times 1 minus I2 times 50 plus 100 minus I, this is supposed to be I1, minus I1 times 1 minus I1 times 20 equals 0. That could be another equation. And then my junction rule, notice this and this come into the junction, but this goes out. So equation 3 would be I1 plus I3 is equal to I2. That's 3 equations, 3 unknowns. You can try to solve this on your own. We'll work on it next time because we're now out of time. You folks are free to go. Make sure you check out the videos on my YouTube channel for more examples. and we'll work more on this and hopefully finish the chapter next time. Have a good one. I'll wait here till the last person leaves.
Have a good night, Professor.
You too. Thanks for coming. Gerald or Shimon, do y'all have any questions? All right, well, have a good one.